All right. Hello, everyone. Welcome to the Off by One security stream, our second of this week. I know we're doing off days this week, but there's reasons for that. But yeah, if you missed Tuesday's stream, go and check that one out. It was really interesting going and looking at some reverse engineering of APT that called Brickstorm that primarily focused on European companies, industries out of China. China was the sponsor of the ABT group and such. But let's give it a moment here while we connect to the different platforms. StreamYard always takes a moment, but I'll go ahead and get started. This week we've got, or today, we have Slava on with us out of Germany, who works in a really cool field in automotive research. So it's always been an interesting area of, I had a couple people on in the past about that as well, looking at connected car security, which is super cool, like Atlas, for example. But Slava, if you want to go ahead and give a little bit of background on yourself, I'm sure folks would love to hear.
Yeah, sure. Thank you, Steven. Hello, everyone. My name is Slava Moskvin. I've been working in InfoSec in this and that role for more than 10 years now. I started as a penetration tester that moved into reverse engineering mostly of industrial IoT devices, and now I work in automotive. Over the years, I've accumulated more than 60 publicly acknowledged vulnerabilities, and for the past year or two, I've picked up interest in Linux kernel, and today I'll walk you through my approach on how we can fuzz it.
Awesome. Yeah. As we were talking about before on the stream before it began, there's quite a few people have been asking for this content specifically. So I was very excited to have Slava come on here. And as usual, if you do have questions, we encourage you to go ahead and post them at any time. If it has something to do with what Slava is talking about or demonstrating, I'll certainly interject and ask. Otherwise, we'll save some of the questions till the end if you have them. But please do feel free to ask it. And as always, this will live on YouTube after we are done here. So I guess, Slava, if you want to tell us a little bit about what you're going to be sharing with us today.
Yeah, sure. So let me actually go ahead and share my screen so
Okay.
we can already have some slides. Because, can you see
All
it?
right, that's good.
Yeah, so today we are gonna, first we're gonna pick a target, a link subsystem we're gonna fuzz. We're gonna talk about KSAM, how it can help us catch some bugs. We will analyze the attack surface, and we will write a custom fuzzer for this subsystem, and we will move through several stages, progressively make it smarter and smarter. And in the last stage, it will have mutations, and it will be guided by coverage. And if demo gods are kind to us, we have a chance to see the fuzzer crashing the target today.
Awesome. All right, sounds good. If you want to go ahead and get started, I'll ask questions as we go through as they come up.
Yeah, sure. So here I have a little bit of a teaser. This is just from the last night when I was testing the thing and just managed to crash the kernel in just under 5 minutes. Okay, so let's go with picking a target. So as we all know, Linux kernel is open source, so you can just go to GitHub or whatever site to browse the source code. And it's already quite neatly organized. You can see all the different folders, like file system drivers, etc., etc., etc. But we often hear that Linux kernel is divided into subsystems. And there is a neat dashboard on the Syscaller website where you can see Linux kernel divided by the subsystems. And what's also cool, you can see how well each of the subsystems is covered by the Syscaller fuzzing. Now we are going to talk about just general considerations. What comes down picking a target, but I think it applies to every security research target as well. Of course, it has to be reachable for an attacker and process some external input. So, for example, file system drivers, network stuff, any sort of netlink-based subsystems, but also things like USB as well. The code has to be fairly, its code base has to be fairly big and very complex. We're not really interested into targets that have just basically a bunch of stubs to make some sort of device work in the system. And of course, there's a question of obscurity of a target. Of course, you get bonus points if you have some novel target or novel attack vector that nobody thought of before. What I also think, if something is hard to research or hard to fuzz, you kind of have a better chance of finding something there because just, most of the people just don't want to bother with something that is hard to do. An example of this may be something that is tied to hardware that is typically harder to fuzz and harder to come up with setups for. And there is always a question, Syscaller always works on the Google service, burning Google money. And yeah, there is a question, should you pick a target with low Syscaller coverage? As you can see here, a lot of the targets has already pretty decent coverage, but as we will see today, it's also not the end of the world because our target has already pretty good coverage, but it will still be possible to find some bugs there. And yeah, I went ahead and I pre-picked target for today's stream. It's gonna be a driver for HFS Plus file system. We're gonna build a fuzzer capable of rediscovering CV 2025-09-27. There was a nice blog post from the guy who discovered it on SSD disclosure. Basically, it's an out-of-bounds write. And what is interesting about it is that you have to be able to mount file system image that you control. And typically, you have to have capsys admin to do that. Or in other words, you have to be root. But the author of this bug, he discovered that on Ubuntu, you actually can mount file system without capsys admin. And this is what allowed him to prove the exploitability and actually write quite an exploit for this bug. Very interesting read. I recommend you to check it out. And just before we dive into the code of our target, important thing is to discuss how we're going to catch bugs. Because historically, you would just fuzz and wait until the target crash. But now we have kernel address sanitizer. And it basically works like any other address sanitizer. So it instruments memory access. It creates a shared memory area. Basically, each byte of shared memory represents each byte of real memory. And bytes of shared memory, they are coded with values 0 to 7, just normal memory. And if it catches access to the bytes with negative values, for example, FF, FE, FC, that when it will cause kernel panic, and it will give you a report like this. I grabbed the screenshot from one of the vulnerabilities I discovered, I think, last year. Here, towards the end of the picture, you see that there was an attempt to access memory that was coded with byte FC. And if we go back, we can see that FC is a red zone between buffers allocated in the kernel heap. And yeah, that was totally what was happening there because the vulnerability was out of bounds read.
Have you done much on the Windows side as well, or mostly on the Linux side?
I've done something on Windows. I did some fighting on Windows with WinIFL, and also have done some reverse engineering of Windows stuff.
Yeah, so for anyone who's done like use something like G flags with page heap, where it goes and puts like additional header information on the front and tracks the origin of when an object was created and add some suffix padding and things like that to check for heap corruption. Very, very similar. Super cool.
Yeah, yeah. And if you want to dive more into KSAN, of course, it's open source as well as the kernel. And also, if you compile the kernel and load it something like Hydra or NIDA, you can see like how exactly KSAN instruments memory access, because like you can compile it with all the symbols available. Something really cool. So the next step is attack surface analysis of our kernel module. And let me open the code. Let me just real quick show the module inside of the kernel code tree. Here, as the kernel code, we have this directory fs, and basically it holds all the stuff related to file system, and also it holds our target. It is, okay, let me do this. HFS plus. Yeah, so here is our target. So I went ahead and I opened it in the code editor. And yeah, the funny thing is that there's like 70% of attack surface analysis of a kernel module like this. You go to the search and you look for something like underscore operations. And oops, no, that is my pre-made file with cheat sheet. Here we can see some struct inode operations. I call it HFS dir inode operations. And the members of the struct, they look familiar to us. Link, unlink, mkdir, rmdir. So what it is, it's actually a structure that holds a callback that kernel calls when you, for example, create a directory inside an HFS plus file system. And there is a lot of structures like that. For example, we have SDIR operations. We have file inode and file inode operations. Yeah, and another interesting thing is super operations, which it doesn't hold things that are typically directly accessible to a user, but it holds something like remount. And I think maybe in the newer version, it also holds pointer to operations that actually implements mount. And here I actually went ahead and compiled all the structures that somehow are of interest for us. We have this dir node operations, dir operations. We also have address space operations, but this is also something that is not, let's say, directly reachable via syscalls. For example, it's right begin and right end. The kernel calls those callbacks when it's time to actually write file to a disk. So you, of course, can reach it somehow, but kind of provides a little bit lower attack surface. The entry operations, also something interesting, in my opinion, because those are called when, for example, you search for a file or you go for a file tree, because the file system is uses this d-entry structure quite heavily, basically like a set of d-entry structures. And those structures are hashed to make access to it a little bit faster. And you can also see there is a compare function that compares the entry somehow. And I think, if you looking, just trying to open a file or something like that, then the file name will go to one of those functions. So next we have like file inode and file operations. What is also interesting is that this structure, it doesn't belong to our search for operations methodology. So this is something to be aware of. This structure holds callbacks to set and get xutters, which is basically xutter. It's like extra attribute you can just set to any file, just whatever you want. And I'm talking about this because this set xutter, it was used in the exploitation of the vulnerability. So this is something that we for sure need to have in our fuzzer. So we talked about looking for operations. Also, sometimes it's not operation, but you have to look for ops, which is, of course, a little bit silly, but also a powerful technique. But we also can go ahead and attack this problem from another side and try to see how the model is initialized and go from this direction. And for this, we need to look for model init, and it will basically register a callback that lets know the kernel, okay, hey, you need to call this function to actually initialize this. And let me show you how it's being initialized. So here, this line is interesting to us, register file system, and you can see it has a pointer to an interesting structure. Structure HFAS plus FS type, which has mount callback. There is some gotcha because this has been recently changed, and if you grab the most recent version of the kernel, the callback for the mount function will be in a different place. So something to look out for. And if you go to the mount function, what is also interesting, we see that there is this mount bdef function from the kernel that has a callback to function that actually does some work as the last parameter. And if you go here, we will see that this function takes superblock and it steals it. So it's definitely doing some work here. And what is also interesting is that we can see how the structures we just talked about are using here. So for example, here it registers superblock operations. And for example, here it registers xutter handlers. So this is another approach how you can start analyzing the attack surface. So a couple of considerations. Of course, we already saw that some structures are filled with this generic file LLC, generic file mmap functions. And it just means that for those callbacks, the module uses generic implementation from the kernel, which is probably not super interesting for us to fuzz. Of course, if you aim for like really comprehensive fuzzer and we want to maybe trigger some side effects, we could and we should use it. But for our little fuzzer, we can just get rid of that to just make it tighter and just be on point. Also, one interesting thing is if you go to callback for IOPTL syscall, you'll see that it actually requires subsystem to move further, basically one of the first line of code in this function. And yeah, it also means that there is no point in fuzzing this function, even if you find something, it will be false positive, because if you have subsystem, then there is no point in fuzzing further.
Yeah, I think that's a question that comes up often is like, how do you
Mhm.
know when you've exhausted most things? And like, how do you know if you've gotten enough code coverage and when it's time to move on to something else? Do you have kind of a way that you determine that?
Yeah, well, of course, I have this question for myself quite a lot. When it's time to start, when it's time to stop. I don't have a perfect answer. It comes down to your experience, but for the metrics, yes, we'll see how we can measure the coverage a bit later. And also, you saw in the syscaller, let me get on the screen. Like on the syscaller dashboard, but actually it's publicly available. So it's the results of Google fuzzing the kernel 24/7. So those percentage numbers are actually the metrics, the coverage, like percentage of basic blocks covered by the fuzzing process. And yeah, if you fuzz with syscaller, you will get something like that right away, but nothing stops you from implementing something like that for your own fuzzer. And we will talk a bit later how to implement that.
Yeah, and like when you use like AFL, for example, the way it does its mutations, or at least when it first came, like walking bit flips, byte flips, doing some random, but with not infinite, but like taking part of a mutation and then adding some random data on the end. Like, do you have a specific kind of way in which you mutate through where you feel confident that you've not only reached the code but tested it properly?
Yes, I steal mutations from IFL++.
Makes sense.
Yeah, so actually, one interesting thing that IFL++ devs done, I think they tested how different mutations, how effective are different mutations. And I don't know if you remember in the original IFL, there were initial steps with deterministic kind of mutations, right? And what IFL++ dev discovered that those steps are not that effective. So they just got rid of that and they don't use it by default. And yeah, if you go deeper into IFL++ code, there is just one big function that just picks mutations at random. And yeah, there is just a ton of mutations, like I think several dozens of mutations there.
Nice.
Okay, so let's continue with the attack surface analysis. Okay, we went over this. Yeah. So on this slide, I have structures that are interesting in our case. I'm interested in anode operations, file operations, and Xatro handler. So basically, we are interested in every callback that is not some generic function implementation there. And as we gonna fuzz older kernel version, we will need this HFS plus FS type structure that I talked about, because it contains pointer to the mount function. And what is actually really interesting is that in the age of AI, one of the things you can do is you can use AI to help you with code analysis and attack surface analysis. So here, just me asking question, just tell me which function is called when the user mounts HFS plus file system. And it has some comprehensive analysis. And yeah, it was on point. It was able to find this HFS plus mount function and actually told me that the actual work is done by this HFS plus fill super function. And yeah, I just discovered that when I was preparing for the stream, something really cool that you can also use in your workflow.
Yeah, that is cool. I mean, somebody did ask a question like how you go about like, do you use AI when fuzzing? Like that kind of question you just asked, like oftentimes you get hallucinations and just incorrect answers. Have you found it to be better and useful on the Linux side of the house since it's open source?
Oh man, I actually have a feeling that it has been trained on the Linux kernel source. Yeah, there was some incorrect examples. So for example, like right now, the current major version of Linux kernel is 6. And sometimes when I ask something, I got question from the kernel version 5. But then I corrected it and I said, okay, yeah, for version 6, it's this, and that. So of course you have to verify everything you get from AI. But yeah, the possibilities here are huge.
Cool.
Okay, so just a little bit of summary regarding attack surface. Just go through the code, look for ops or duration structures. You can also look up for syscall names. You will find them eventually. You can also just start analyzing the code from the moment of model initialization. And yeah, you can use AI to kind of guide you through it and make your job easier. Yeah, and here, those are syscalls we are going to focus on. We're gonna, of course, we're gonna need mount because from the blog post we know that on Ubuntu you can actually find an exploitable vulnerability that uses mount. ioctl we're not gonna use because it requires capsysadmin. We will use create and kadir, link, unlink, set, etc., and some other syscalls. Yeah, and here now we are starting with demos. Our first stage of the fuzzer is just really dumb fuzzer. We'll mount the file system and we are going to execute some syscalls. I think I can close this one. Yeah. Yeah, so let me know if I need to zoom in my screen more. And here I'm just gonna walk you through the source code real quick. We have fuzzer.c with the main fuzzing loop, and we have fuzz syscalls just with syscall stuff that we are gonna fuzz. Yeah, so first of all, just to start with, we are gonna create a file and just fill it with random crap. And later in the fuzzing loop, we'll try to mount it. If the mount was successful, we will execute our fuzzing functions that are determined in fuzz syscalls. Yeah, I have just some wrappers around actual syscalls, like you can see fuzz open. I generate random paths as an argument with flags. Okay, I just hard-coded it. But of course, it will be better to fuzz them as well. And yeah, we have fuzz encoder, fuzz link, fuzz unlink, and most of the parameters are generated randomly. And yeah, there is this array of function we are fuzzing, and we'll just go through this array and choose function randomly and execute it. You can see that there is this step, checking for bugs. I decided to not implement it for stream to keep the code base smaller, but in real life, you will definitely want to implement some sort of function that it can just go through the kernel logs and look for case and message or for kernel bugs messages. But for now, we're just going to monitor the kernel logs ourselves. Yeah, so that is the gist for it. Just generate random file system image and mount it, change directory to the mounted file system and execute some random syscalls on that. Okay, so let me go to the directory of the fuzzer and let me build it remotely on my Linux VM. And yeah, I will go here. So I will need sudo for fuzzing because yeah, it will make our life easier with malking and stuff. And yeah, as we can see, via fuzzing, it was essentially a light speed, more than 3,000 iteration per second. So it would be interesting to see what is the reason for this astonishing speed. And if I go ahead and I just enable login in the fuzzer and I rebuild it, yeah, we will see that basically on every iteration, we have mount error. Because of course, the file system just don't want to mount the random stuff we put inside it. The file system image is supposed to be really, really structured. So yeah, this just not gonna cut it for our fuzzer. And here is yeah. So here is when the corpus clashes comes up. So we need to start from some real good data. And of course, as we are going to mutate it later, typically we want inputs that are as small as possible, but still contain all the interesting structure. And here I discovered that with HFS++, we can just go through trial and error and try to make a file image that is as small as possible. So here you can see I try to make a file image that is just 500K in size. And but I couldn't mount it. No, I couldn't even create the file system image. And yeah, the MKFS was quite enough to tell us, yeah, that this partition is too small and we need just 12 kilobytes more. So I went ahead and added that. And here we can see our file system image that we are going to use in our fuzzing process later. This HFS plus .image.saved is just will be the reference image, and I will copy it to .image.fuzz for us to fuzz, because for sure those system calls that we are calling on the image, they will change it. So let me just copy it. And what I'm gonna do now is I'm gonna tell the fuzzer to use not just random images it can create, but to use this real image and try to fuzz system calls inside this image. Oops. I think it would be better to disable logs for this. Yeah, and now we can see that our fuzzing speed is actually on an order of magnitude lower. And this is because before that, our fuzzer just didn't do any actual work. And now as you can see, if you're doing some work, yeah, I think goes slower. And yeah, here is actually when we are going to introduce coverage to our fuzzer. As our fuzzer is done, it's not going to use it just yet, but we're going to use it to measure the fuzzer performance. For that, I have the next micro stage of the fuzzer, the stage that actually supports coverage. You can see there is this coverage.c files that actually implements coverage via kcov. First of all, I wanted to just walk you through the further code and tell you what has changed. So this is basically the main use of our fuzzing loop. And before that, you can see there is some coverage start function. And after that, you can see there is some coverage stop functions. And even before this loop, we have, this coverage init. So let's take a look what's inside this. And inside it's just the code that is basically copy-paste from the current documentation. There is very neat documentation for kcov online telling you how to use it. You first have to compile the kernel with kcov, and we'll get to that in a moment. But once you do that, you will have this sudo file that you have to open. Then you just execute an directory on it, telling you, hey, I want to initialize kcov. And then you have to create a shared memory area that will actually hold the coverage. And the coverage in our case, it will be just a set of program counters in the order they've been hit during the execution. And for starting the coverage, the main thing that starts it is a Yocto kcov enable with cov trace PC. There is a different method for enable remote coverage for kcov that is useful. And for example, you're fuzzing some things that exist in the kernel as separate threads. But in our case, we'll just use that. And also one thing we want to do is we want to reset the coverage counter, which actually is the first few bytes of the memory area we just allocated. And in the coverage stop is just this kcov disable ioctl and just a little bit of housekeeping. And in the end, there is this coverage check function that is a function we implemented because we need to process coverage somehow and extract useful data. So first of all, we are loading the number of program counters that were hit. For this fuzzer, I chose to implement just very, very basic coverage metrics that we are going to mark each basic block that was hit during the execution. You can experiment with different metrics yourself. You can, instead of marking basic blocks, you can count how many times they were executed. So for if something is executed in a loop and you want to see, you maybe want to go further in the loop, or actually you want, you can implement edge coverage if you hash the program counter some way and then combine them.
Yeah, I was going to ask how much overhead the instrumentation and all that causes with KCOV.
We will see in a moment. Quite
Okay.
a lot, actually.
Someone was asking, is that a real HFS image or a fake one created from dev0?
No. So right now we are going with the real image.
Right.
We saw that, just random or dev0, they just won't gonna cut it. They won't be unmounted.
Right. Cool.
Yeah, and here you can see how we comparing the coverage. I have this current coverage. It's basically like a byte array that holds current coverage metrics, and I also have best coverage. And if we have hit at least one basic block that wasn't stored in the best coverage, then we tell, okay, we found something new. And this is probably interesting. And this is what's going to come into play later. But right now, let's launch the fuzzer with coverage, and we'll see how it will affect the performance. Okay, so let me go the directory. And first, let me just launch the fuzzer with random image. And yeah, you can see that just even with a random image, the speed is probably 50% or twice as lower. And what is also interesting is that you're seeing that we are getting somehow new coverage, even though we are not doing any real work. And it's just like 1, 2, or 3 points of best coverage at a time. That is a really interesting side effect. What I'm thinking is that just because we are going through a lot of iterations of that, it's just some random stuff in the kernel that is being triggered during the time that we are doing that. This probably has nothing to do with the actual HFS plus. And now let's try to do fuzzing with our legit HFS plus image. Yeah, and we can see that, yeah, it's much slower than fuzzing without coverage, and the speed actually goes down. In my experience, it settles for at least for the stage 3 fuzzer, it settles around 70 or 90 iterations per second. What is also interesting is that you can see that coverage is also growing, but it grows sometimes by 10, 20, whatever, so like 100 points at a time. And I think it means that we are actually hitting some logic in HFS plus, and that is what's doing it. Of course, we have talked about this coverage as just some things, just we are calculating. We have in theories why this or that is happening, but we can actually find out for sure. And for that, I have something called KCOV test, just as a program that will execute some actions under kcaf, and then it will tell us the program counters of basic blocks that have been hit during the execution. Kcaf test. Yeah, and you can see, yeah, there's been quite a lot. But of course, it doesn't tell us much. We can load it in IDA or Ghidra and try to see what's happening there. But there is actually a better way of doing this. There is something called address to line, and if you have kernel compiled with symbols, you can use this. And it will actually provide us information with actual lines of code that have been hit. And this is a great way to debug your fuzzer and figure out if you're actually hitting any sort of logic inside your kernel module.
That's really cool.
Yeah, thank you.
Someone's mentioning, I think there could be a bug with those atomic relaxed. The one in the loop can be reordered CPU and loaded before NCNT is loaded.
Well, that is something that's definitely good to know. I didn't think of that. I suck at atomic operations, and the reason I'm using it there is because I used in the kernel documentation.
Nice.
Okay, so let's check out the slides for the moment. See if we need to cover anything else before moving forward. Yeah, I think we should also talk a little bit about compiling the kernel. This right now, maybe it comes a little bit out of order, but I wanted to show you something interesting first. Compiling the kernel is really easy. Just, you can execute this tiny neat small command to configure it. But actually, it's not that complicated. The first thing you want to do after you download the kernel source code, of course, you install all the dependencies. Then you execute make devconfig, it generates .config file with just default parameters. And what most tutorials teach you is that then you go through this .config file and you enable everything manually. But what I found out, there is this neat script, which is also in the kernel source code tree that allows you to just enable those parameters programmatically. Yeah, one important thing here is you can see here -e, and -e means that it means enable, and anything with -e will be compiled in the kernel statically. And we want to compile everything statically for fuzzing because it will make our life easier with with SLR and with coverage and with comparing coverage and stuff like that.
Yeah, and on that, someone's asking, is it possible to discover the addresses of the functions it uses? Kind of like how you were showing the source code information. Can you also discover what addresses are hit and used?
Yeah. So you can just dump these program counters and run this through address to line utility. You can do it even just during the fuzzing to get a better idea of coverage. Also, I think somewhere in this command we tell the configuration to enable call sims. And I think you can also use call sims to get the address of the functions you're interested in.
Cool, thanks.
Yeah. So obviously, one of the most important things, we want to enable kcaf, we want to enable ksum. And we want to enable our HFS Plus kernel module. And we want to enable all the dependencies of this kernel module. And the sole dependency of this module is something called block. And also something really neat is you can add an arbitrary string that will be added to your kernel image name. And it makes my life much easier when I see all the kernel names in the graph. I have no idea like which one I have to boot into, and just add in a little string in there and just helps a lot with that. Yeah, here you can see how you can actually go through all the dependencies of a kernel module. Inside every kernel module, there is this file called kconfig. And you can see here on the line number 4, that depends on block. So, this is how we know we need to enable block as well. Then you just make all config to save our config file, and just basically make and install commands after that. What this also helps is to configure your bootloader or whatever thing you're using to load the kernel. You want to use kernel panic on warn 0 and kernel panic on ops 0 in your kernel command line to prevent the kernel from rebooting when kernel panic was triggered, because we don't want to reboot. We want to read those kernel logs and see what happens and save our crashing input. Yeah, and this just something circling back to kcaf. This is the link you can use to get more information on kcaf and how to use it in the kernel. I will share the presentation later, so you will have all that. Okay, so we actually went through this kcaf test. We compared performance. We compare performance with the legit image. And yeah, we already, oh yeah, we have the next, stage 1 fuzzer. Yep, sorry. Yeah, so now it's time for another demo. We are going to develop the second stage of the fuzzer. And the most important thing about this stage is that we're actually going to generate better seeds for our fuzzing process. You can see there is this new file, generate seeds.c. And here is what we are doing is we are starting by mounting a legitimate file system image. And then we are just executing all of our syscalls inside this image. But then we are not discarding this image. We're actually saving it in our seeds seeds folder. And what makes it better is that our initial file system image that we are fuzzing, they will be already much more diverse. And this will boost our fuzzing capabilities just drastically. So let's change the directory to generate seeds. Let's build it. Let's change the address on the VM. And let's start generating seeds. Yeah, here you can see in the command line, I'm going to use my saved HFS+ image as a base for generated seeds. And I'm going to save them in the generated seeds stream directory. Let me go ahead and check that this directory is empty. Nope. Then I need to clean it up to make sure that this is all fresh. Yes. Okay. Yeah, I need to use sudo. Okay. Okay, so let's go inside our seeds. We have 20 of them. And let's try to mount one of those and see what's inside it. Yeah, you can see there is a lot of random stuff in here. You can see there is also some sync links here, for example. And yeah, in general, this is much better fit. That is much more interesting to fuzz. And now we can actually try to run our first generation fuzzer, but instead of just this boring, practically empty seed that we used before, we'll try to use one of those and we'll see how it affects it. Yeah, so you can see it's much more slower again. I guess because it requires some additional work in mount and requires some additional work in executing syscalls because there is just much more stuff going through. And you can see that, yeah, even though the fuzzer is done, somehow coverage points are slowly climbing up. But the most interesting coverage metrics we will see on the next stage.
It always feels like it's doing more work if it takes longer, so that's good.
Yeah, exactly. You don't want to do your work too quick. Okay. So let's check with the slides. Yeah, it's basically all demos from now on. So let's move to the fuzzer stage 3. And yeah, here will be more going on. We already know the coverage thing. We already know fuzz syscalls. You can see that, yeah, our main fuzzing loop, we are still using the coverage. Some stuff happens between coverage stop and coverage stop. We still mount the image, change to dir, and execute some syscalls from our fuzz functions array. But then we are doing something interesting. If we have found new coverage, we will save our modified file that we have mounted. And we will save it into the directory with all the seeds. And this way, we are making sure that our seeds include file system images that have progressively more and more coverage. And yeah, of course, this is what you typically want to do. achieve more coverage. So let's build this thing and see how it's running. So I'm going to tell it to use the seeds we have just generated. And yeah, it will mutate them, and we will see how it will improve our coverage. And actually, yeah, we can see that we are fuzzing much slower, but we already have coverage that is much better. Yeah, so we lost some iterations per second, but we gained in the coverage. What is also interesting is to see what is happening inside the kernel logs. Uh-oh. Maybe something already happened. No, not yet. But you can see that it's already behaving a little bit weird. My SSH is not connecting. Sometimes it could be a sign that something has crashed, but I can't see it in the VM console. Yeah, well, we can use the VM console as well to monitor, because all the most important stuff, anyway, will end up here. What is interesting, you can see there is some messages we are getting from HFS Plus. Failed to load root directory, failed to load extents file. So something is definitely happening underneath.
Someone's asking, what are the best practices for isolating Linux kernel modules during fuzzing to avoid noisy coverage or interference from core kernel logic?
Yeah, so one approach is just don't do that and make sure that there is not a lot of stuff happening in your kernel. Just remove anything that doesn't have to do with your fuzzing. Typically, like if you go to syscaller docs, for syscaller, you're basically required to build your own VM image that has just absolute minimum of stuff going on. The second thing is that you're getting program counters from kcuf, right? And because we are usually disable ISLR when we are fuzzing, the kernel will be loaded in the same base address on each boot, and gives you an opportunity to filter those program counters. Just you have to just figure out the address ranges where your module resides inside the kernel, and this is some filtering that you can also implement. I try to do that, but in my case, my target was just all over the kernel, and I had just, I know, dozens or hundreds of ranges I had to care of. So I just decided to not.
Cool, thanks.
Okay, so I ran this fuzzer a couple of times today, and it was able to produce some crashes in under 5 minutes of fuzzing. But of course, right now we are starting fresh, starting from the new seeds. So we will see if we have something like that, and if the demo gods are kind to us this way.
I think everybody prefers live instead of recorded because everybody runs into problems, and the demo gods, they're always there. So working through those problems and such is always good practice.
Yeah. Just in case, I have a cross example saved in the slides. But yeah, we can give it a couple of minutes. Otherwise, this is all I had today.
Cool. Well, since we're waiting, I'll ask a question from someone. How do you compare? I'm not sure. You said you've done some Windows stuff, so I'm not sure if you're going to be able to give an answer. But how would you compare the complexity of heap internals and exploitation on Windows versus Linux? How strong are heap protections on Linux, and are they enabled on IoT devices in your experience?
Yeah, so I'm not that well versed in mitigations because just historically I have more experience with finding bugs. About the last part of the question about IoT devices, when I just started doing IoT, there was probably zero mitigations. But nowadays, devices get more powerful and they also get more attention. There's, of course, some regulators in different fields. So we're definitely seeing more and more mitigations being enabled in IoT devices.
Yeah, especially with things like ARM memory tag extensions and stuff. Those really changed the game.
Yep, exactly.
Yeah, and on the Linux side, there's obviously the heap attacks against the metadata and like the heap manager itself, kind of like the old safe unlink attack before it was there, Tcache poisoning, going after that stuff. And then on the other side, there's the heap data attacks, of course. And I haven't done, I know some people who could answer really well around the mitigations effectiveness on Windows versus Linux. But obviously Windows is pretty far along there with the segment heap and the low fragmentation heap and all that good stuff.
Yeah, so while we waited, we actually managed to gain quite a lot of coverage points here. Just in a couple of minutes means more and more stuff being hit, and we are probably getting closer. The bug, you can already see that we started hitting some weird errors like inconsistency in B-tree, request non-existent node in B-tree. Yeah, I know something is coming up.
Someone's asking
Yeah.
on black box devices, when do you decide to fuzz, when to reverse, or do you do them simultaneously? Like, what's your thought process? Like fuzz first, reverse engineering first, combination?
I would say the best way is to just start with a rough fuzzer and reverse engineer the logic and try to improve your fuzzer by inserting this logic into that. But I typically start first with reverse engineering. Seeing the logic, just seeing if it's worth fuzzing, is the logic complex enough for fuzzing, or maybe I can just read the code and it would be just faster than kind of with a fuzzer, or maybe there are some logical vulnerabilities. And anyway, you want to do at least some reverse engineering to improve your code coverage. For example, like it's classics, you have some kernel model for some weird peripheral. And the typical communication channel is through ioctls. And of course, through ioctls, you have to know the command number. And I mean, if you want to brute force the command number, I think it's like 4 or 8 bytes. It would take a long time to brute force all of them. Just easier to just reverse engineer and grab those commands from it.
Yeah, a lot depends on the bug classes you're looking for as well. And
Exactly.
one benefit to AI is like if you have to write an RPC client or something, you have that help now. Like in the past, you identify an attack surface. A lot of times you need to write a client or server, and that can be very time consuming to spend the time understanding what file format you're dealing with or what network protocol you're dealing with, all that good stuff.
Yeah, exactly. With AI, you can create fuzzer, at least a very basic one, in just no time.
Yeah.
But yeah, while we were talking, there is some exciting stuff happening here. Let me scroll to the first message. Oops. Yeah, the reason it prints more and more stuff is because I have a lockup detection enabled. We can see that we have hit kernel bug. This is not a KSON report, but either it's kind of like an assertion in the kernel. We can see that the kernel crashed our file because of that. Now I can actually go to the message and show you to you a bit better. And we can see we have generated a lot of logs here. Warning. So we had the warning first. Yeah, and then we had a bug.
Nice.
And the nice thing, it really tells us the exact line. So let me go ahead and open this file, it's bnode. What was the line? The line was 618. 618. Yeah, here you can see bug on. So it works like assertion. It causes kernel panic. In this case, we can see that the reference counter for the node was 0. And this is why the assertion was called.
So use after free or what?
I'm not sure. I was thinking about that. I don't think that by default we can move fast past this bug on because it causes kernel panic.
Yeah.
At least in the desktop Ubuntu. This is older kernel version, but just it's 6.11.9 because judging by the report, the bug we were trying to find was fixed in 6.12. The current version is something like 6.14, 6.15. So it would be interesting to see if it's still present here and if we can really trigger it on Ubuntu as a normal user.
What is your process for determining whether or not something could potentially be exploitable and worth like trying to get a CVE out of it versus just a bug?
I would say exploitable and CVE are two different things. You can get CVE for almost anything these days, I think, as long as you have some sort of public information about the bug, even your blog post, I think, would suffice. Yeah, in this case, I would say if it's possible to trigger that as a low privilege user, that would be a local DOS, which is like not that interesting, but probably possible to get a CV out of that.
Yeah.
Yeah.
Yeah, it's like, part of the vulnerability research process, I get asked these kind of questions a lot. It's like, which part's the hardest? Is it the hardest to find a bug? Is it the hardest to like determine if it's exploitable? Or is it the hardest to actually get a working exploit and deal with all the mitigations? I mean, all of them have their own challenges, but it's multiple steps.
Yeah, I can imagine it also depends on your target and your approach and all the different factors.
The time before mitigations, that's what I call the golden age of exploit development, because that can be the worst. I mean, it's very humbling and frustrating trying to get around HVCI and ASLR, and you got to get a chain going with the info leak bug as well. And
Yeah. And some people, they just don't want to bother with that. I used to see like, I still think that the kind of lower you get into the system, if you get to the lowest of the levels, it's where you see or where you don't see a lot of mitigations.
Right.
Like, some years ago, when it was novel, some guys hacked, I think it was like virus chip on iPhone. And of course, iPhone by then already had a lot of mitigations, but the virus chip had none. So yeah.
Cool. Yeah, it's great stuff. Is that the end of what you wanted to demo and share, or?
Yes.
Okay.
This
Yeah,
is
it's fantastic stuff. Again, a lot of people have been asking for this, and it's very generous of you to share kind of your process and explanation around everything from compiling the kernel to writing the fuzzer and modifying things and showing the crashes and all that. I think a lot of people get some really good value out of this, which is awesome.
yeah, Steven, thanks for having me. Yeah, had a really great time on this stream. I will share the source code a little bit later, along with the presentation.
Great. Yeah, if you want to send it over to me, I can put it and tag it in the YouTube video after it's posted up.
Yeah, sure. I think, yeah, once I have time to clean it up, I'll send it.
Yeah, thank you so much. I mean, I can tell you put a lot of preparation into this and stuff, and would love to have you back on again if you ever have something interesting you want to show us.
Yeah, sure. Would love to get back on. Yeah, thank you.
All right, thanks everyone. We'll see you next week. Appreciate it. Bye-bye.
Bye.